Thank you. I apologize for the delay. Zoom decided to update as soon as I logged in, and you needed privileges and all these things. So I'm glad I was able to join. And thank you also for the invitation to talk in this series. So today I'm going to present our, and also the nice introduction to tephrochronology, which I'll also be discussing. Today I'm going to present our work on high-resolution geologic mapping and tephrochronology at a very important paleontology and archaeology site in the Afar Depression, where Plio-Pleistocene age sediments are narrowly exposed in sedimentary basins among the faulted basaltic ridges that really characterize much of the floor of the Afar Depression. And we are using these methods of geologic mapping and tephrochronology to not only support the ongoing paleontology and archaeological work, but also to learn about the rifting processes that drove that sedimentation. So here, this is a photograph of my favorite area in the Ledi-Geraru site, where the Mile River that you're looking at has incised this package of laminated lake clays shown here. And each of those white lines, you can see one here and then up through here, each of those white lines are an individual tephra deposit that was deposited in this lake. And we use those tephras for correlation as well as for dating the sediments. And you can see this nice fault and fault wedge here offsetting those units. And then in the background are much younger, coarser, and fluvially derived sediments and paleosols. And this really reflects the change in the basin configuration and the depositional setting that we see in the region. So first, I just wanted to highlight our dedicated and really hardworking geology team shown here, and then our paleontology team, which is much larger than just the three folks that I'm showing here, the archaeology group that works at Ledi-Geraru, and then our Afar colleagues, as well as our extremely talented support crew that makes working and living in the Afar so enjoyable. And this is our photograph of our latest field season in February of this year, and then just acknowledge the funding that has supported this work. Okay, so this is a map of the East African Rift from kind of Lake Malawi here in the south through to the Afar Depression. I'm showing these very large border faults as well as the placement of volcanoes in the area, and this really long history of rifting and extensional rifting and volcanism is preserved in the sedimentary basins that were created by the rifting processes. And this is also where ongoing human origin sites are located. You can see those in the orange within those rifts. And so if we want to understand the geologic context for human origins research and study the depositional environments and paleo landscapes, we really need to know about the timing and the mechanisms of basin integration in the area. So we're going to focus in on the Afar Depression shown here in that black box. Okay, so here we see this really incredible topography of the Afar region. This is a DEM draped on a hillshade of the area, and you see these deeply dissected volcanic highlands, these marginal basins here where a lot of the tributaries to the Awash River originate, and then the volcanic centers, kind of these conical centers through here, and the really complex faulting patterns from the on-land extension of the Red Sea and Gulf of Aden rifts and the northern extension of the main Ethiopian rift into the Afar Depression. And so the sediments preserved in the sedimentary basins kind of along the Awash River contain some of the most important fossils for studying human evolution, including the discovery of, here we go. Including these discoveries in the lower Awash Valley, which I'm showing in that purple rectangle here. So these include fossils like Lucy and Salam and some very old stone tools. And then more recently, the discovery of a mandible of what is thought of as the earliest Homo fossil, around 2.8. And this is a really important, and this was discovered in the Ledi-Geraru paleontology site. And this is a really important discovery because it, this time period for human evolution, it's a really important time period for studying human evolution because there are very few specimens at this time. So in this talk, I'm going to focus on the geology at Ledi-Geraru, located here where that star is, and this is within the lower Awash Valley. And this area has been structurally influenced by kind of the northern migration of the main Ethiopian rift and the triple junction to the location, its present location near Lake Abe. And so we see that manifest in the changing basin geometry that we've interpreted based on faulting patterns that we've mapped in the Pleistocene sediments and basalt flows. We interpret that the basin likely followed or could have been constrained by a northwest-southeast fault following more of the Red Sea Rift trend early on, where we had this quite large Lake Hadar that was expanding and contracting following climatic drivers through time, and then it's changed to more fluvial deposition that might have been around 2.6 that may have been related to a change in the basin geometry following more faults related to the main Ethiopian rift. So unlike other areas of the lower Awash where the stratigraphy is more straightforward and for where there are very few faults, for example here at Hadar where we have this nice layered stratigraphy, the prolific faulting at the Ledi-Geraru site really requires high resolution geologic mapping as well as those tephrochronology to accurately place the fossils and artifact discoveries within the correct geologic context. And I'd like to say that these faults also really afford us the opportunity to learn about rifting as well. So these are 3 photographs of examples of faulting patterns. Here are some diatomaceous silt faulted against basalt flows. Here you can see these layers of tephra within lake clays that are faulted, and then here again this double tephra deposit here that's been faulted as well. So we are doing this by using small UAVs to collect high-resolution imagery in order to generate orthomosaics and digital elevation models. And this work has been led by David Fury and Ramon Aerosmith at Arizona State University. And we're using this data as base maps for field mapping. So we are using StraboSpot mapping software on iPhone and iPad platforms to collect our digital geology data, and that data is then integrated into ArcGIS Pro software. So this is an ortho image of the area. You can see this really nice fault through here, and this is a nice marker bed that we've used. It's a green clay with a double tephra layer that's right above it. And then if we look at this is a hillshade from the 6 centimeter digital elevation model that we use for mapping. So if we look at our Strabo mapping, here is this yellow line is the trace of a tephra deposit, this golden sands tuff here. And so we're also using tephrochronology to analyze major and trace element geochemistry for correlation purposes. So this is just an example of some of our correlation efforts, just showing the major elements here. And then also using these tephra deposits and dating feldspars from them to learn about the timing of the deposition, the timing of these eruptive events in the area to date the sediments and therefore date the fossils and artifacts. And from this work, we have interpreted a chronostratigraphic framework for the Eastern Ledi-Geraru with deposits ranging, and it's kind of hard to see from the Pliocene here at about 2.95. They're sitting just on top of a stratoid series basalts up into about 2 million years here where these sediments are more fluvial in character, and we've identified kind of a major unconformity surface around 2.6 million. This is an example of the application of 3D mapping and tephrochronology to constrain the potential source areas for fossils found at the surface of a paleontology site. So here we are looking at an oblique view of mapping of 3 different dated sedimentary packages: the green, the blue package here, and the orange package here, and the Kora basalt flow. And these sedimentary packages are faulted against the Kora. And this is all sitting on top of a hillshade derived from a 6 centimeter DEM that's overlying here an ortho image created from UAV work. And so what this figure shows really well is that the fossils at this paleontology site were not eroded from this older Garumaha sediment package. So we can rule that out as a source area for the work done at this paleontology site, but rather these fossils were derived from fossiliferous units that are just below this dated Ledi-Geraru tuffs at 2.63 million. So we have a better sense of the location of where those fossils were derived. And we can see that nicely in that the channels that are eroding from the Garumaha sediment package are flowing away from the paleontology site. So here's a geologic map and cross-section from the early Homo site. This is the photograph of the mandible that was discovered here. And what I'd like to point out here, this is the geologic map and the cross-section. And what I want to point out here is the really narrow fault blocks that we see. This is 125 meters to a few hundred meters. And these are separating some quite large faults as well. And then those faults are placing sediment packages of very different ages right next to each other. And so when we're out with paleontologists and they're collecting fossils on these surfaces, they need to know what age to assign the fossil. And this requires very detailed geologic mapping. Oftentimes we're mapping at less than 1 to 1,000, and now more likely like 1 to 3 to 400. And so while these prolific faults seem like they would be a complication and complicating these efforts, they actually provide an additional check on our tephrochronology efforts, whether or not we have faults that align with the dates of those tephra deposits. And they also provide constraints on rifting processes in the area based on what fault sediment package they're offsetting. And this is just a hillshade showing the traces of the volcanic ash layers on top of that very high resolution hillshade. So old limestone tools were also discovered in the area at all places, right at the intersection of 2 prominent faults in the area. This is the northern extension of this Kora basalt, and the fossil or the artifact discoveries are right here. And what we're seeing is this intersection has uplifted this block, and you can see the tilt of the sediments at about 35 degrees here, resulting from that faulting, and then the location of the BD1 archaeological site. So here, working out the 3-dimensionality of the geology was really important to show the projected stratigraphic position of the Ledi-Geraru tuff, which is the tephra deposit that we dated to constrain the age of this site. So we needed to understand the 3-dimensionality of the folding and the fault patterns here in order to use that date to constrain the ages of that artifact site. And then just lastly, zooming out, we can view the geology map for the Ledi-Geraru area, where we have mapped both northwest southeast trending faults as well as northeast southwest trending faults at affecting different parts of the stratigraphy through time. And so what we've done is focus our initial high resolution mapping efforts on some of the fossil and archaeology sites that are shown here in the stars over the locations of the previous 3 slides. And in upcoming field seasons, what we do is hope to expand those efforts to better capture fault interactions at different locations throughout this mapping area, which will help us inform and revise the basin models, which I'm trying to get up. There we go. So to use those mapping efforts to kind of refine these basin models. Thank you.
Thanks, Erin. That was really good. Are there any questions from the audience? Just raise your hand, please. Okay, good. There's one hand. Yes, so Celine, go ahead.
No, I was just clapping.
Oh, okay.
Easy.
Sorry. Are there any questions? Otherwise, I can ask one or two. Okay, thanks. So, Erin, are there any constraints from where the volcanoes are that are sourcing these deposits? I guess they're quite old, so maybe not, but what?
um, no is the short answer. We have long thought that there's a volcanic center actually in this just to the left of where the L is in Lake Hadar called the Idi Ali Volcanic Center. And a lot of the more proximal tephras we've assumed have come from there just based on some preliminary geochemistry work. We've kind of linked one of the older tephras, the 2.95 million that's found in the area, to that volcanic source. But other than assuming that some of these tephras are originating from there, we don't really have don't have good constraints geochemically from potential source areas kind of outside of that location.
Thanks. So also, how's the sort of the stratigraphic relationship between these deposits and the stratoid? I guess the lower stratoid deposits, are they just spatially separated, or what's the
We
link?
see the record here sits right on top of the stratoid basalt. So we see some areas where they're very thick, 3 or 4 very thick flows of basalt, and then we see diatomaceous silt sitting right on top of it. So we see a lake basically right on top of the basalt flows. And we see that in other parts of the Ledi-Geraru site as well as from there was a drilling effort throughout East Africa, drilling different hominid sites. And they also have noticed quite a bit of basalt with laminated clays and diatomite sitting on top of it. So we know that their basalt flows were flowing into lake, and here being Lake Hadar. So we do see that, yeah.
Okay, and for Lauren?
Yeah, I'm gonna go quick. Thanks for the great presentation, Erin. A quick question. The map you're showing on the left shows two faces of northeast trending faults. Is there a way to tell which one is older from the map view, or do we just have reactivation of the oldest face?
Yeah, so we know some fault. We know the timing of some of the faults. So the kind of I'm showing in the lower part above that pink area, we have faults trending northeast, southwest, and we see those right along here. And we, for example, let's just take this fault. We know that that fault does not continue, or we don't see that fault continuing through here and offsetting sediments that are dated to about 2.8 million. So that fault had to have been active after the deposition of the pink sediments here, which are dated to 2.95, but prior to the deposition of the sediments that are 2.8 million. So we can get some constraints on the faulting. And like I said, we have mapped in detail some of these areas, but we're kind of continuing to work out the structural details of this mapping in other areas.
All right, thank you.